Alright, let's get started. So, in some ways, imaginary numbers work a little like surds. For example, if we had 2 plus 3 root 5, and that equaled a plus b root 5, would we be able to tell what a and b are?
Yeah. Yes.
Yeah, so you've looked at equality with surds before. We know that a is 2 and b is 3. Alright, similarly with imaginary numbers, we can say that if we have a plus bi, and that equals c plus di, then a equals c, and b equals d. Now, the proof for this is the proof by contradiction I mentioned yesterday. So here we start off with the premise, or the starting idea, that there are two states. Either this is correct, this is true, or it's not true. So you can either have one or the other. There isn't any other option there. It either works or it doesn't. Alright? And now we suppose that it doesn't work. So we suppose that b is not equal to d. So we can suppose, or we can write assume. No. So it's a bit like tossing a coin and then assuming it's a head. Alright? If we toss a coin, assume it's a head, and then we have a look at it and it's not a head, therefore it must be a tail. Here we've got two options. Either it's equal or it's not equal. We're assuming it's not equal, and let's see if that works. Alright, so assume it's not equal. Then we have, you don't have to copy this down, but try and follow the logic as we go. If we have a plus bi equals c plus di, then we can do some rearranging to get all the imaginary parts on one side. So it becomes bi take di equals c take a. Okay? And then we can remove I as a common factor on the left-hand side. B take D equals C take A. Find me some space. Oh. Then we can divide the factor of B take D over. And the only reason we can do this is because b is not equal to d, and that's what we've assumed at the top. If b was equal to d, then we'd be dividing by 0. And have I shown you all know why dividing by 0, it's a bad thing in math. That's one of the axioms I mentioned. You cannot divide by 0. Have you seen the proof for what happens when we divide by 0? Ah, that's interesting. Okay.
I'll put an instrument lesson now.
Huh?
I'll put an instrument lesson.
Alright, you've got to go. I'm recording it, so you'll be able to watch. Alright. This is actually good practice for factorization, which we're doing currently anyway. Somebody choose a number. It's a bit like a magic trick. Choose a number that's simple we can work with in our heads. 7. Everyone chooses 7. Alright, we'll have 7. Alright, let's make a equals 7. And b equals 7. You don't have to copy this down. This is in no way related to imaginary numbers, but you're welcome to. A equals 7, b equals 7. Alright? Would you be happy with a squared is equal to b squared?
Yeah.
If they're both equal to 7, they're both 49. And then would you be happy that that is equal to a times b? Yeah, because a and b are both 7, so a times b, 7, 7. Alright? If we're all happy with that, could we say that a squared take b squared is equal to a squared take ab, because b squared is equal to ab? You can feel there's a trick coming on, but no one's quite sure where yet. Alright, how do we expand that left hand side if we have a squared take b squared? Sorry, factorise, yeah. Good, so this factorises out to a plus b, a take b. How do we factorise the right-hand side? Common factor of A? Now, across each side, there is a common factor, yeah, of A take B. So we get rid of it. We can divide out by A take B, leaving us with A plus B equals A. Now that looks weird, because we know we can we can subtract A from both sides, and therefore B is equal to 0. Which is an issue, because at the start, B was very much equal to 7. So what happened? Have we eliminated every number and reduced everything to 0? Or what went wrong? What went wrong is that we broke one of the axioms. We went against this law where we can't divide by 0. When we took out this common factor of A take B, because A is equal to B, we divided by 0. So if we allow dividing by 0, we can do this step, and everything in maths we can reduce to 0 like we've done to B. And this is why we can't divide by 0, because otherwise all of a sudden algebra doesn't make a lot of sense, because any number can be reduced to 0 using a similar trick to this. Right? And this is just one of the laws you're not allowed to break. You can't divide by 0, and this is what happens if you do. Alright? Everyone make sense of where that algebras all come from, and then the trick? It's kind of cool. And that's why in our proof by contradiction, if we assume that B is not equal to D, then we're allowed to do this division. Alright? And if we're allowed to do this division, then we've shown that I is equal to C take A over B take D. And C take A over B take D, they could all be real numbers. C, A, B, D could be 1, 3, 5, 7, and so on. And we know that I is not equal to 1, 3, 5, 7, or whatever it becomes. So if we're allowed to do this division, I doesn't hold true. Like what we've defined for I, what we define I as the square root of -1 doesn't hold true. So we've shown that if B is not equal to D, it goes wrong, and that I is not equal to (-1), or the square root of (-1). So we've effectively contradicted ourselves. We've shown that if B does not equal D, then I doesn't hold true. So therefore, if B does not equal D, and that doesn't work, the other option must work. Therefore, B must equal D. Yeah? We've had two states. We've assumed one state. We've assumed that B does not equal D, and that doesn't work. So it must be the other. B must equal D. Okay? Good news is, if you aren't entirely comfortable with that yet, you can still do the algebra that follows just by taking it on faith. Alright, so if we have this A plus BI equals C plus DI, then A equals C and B equals D. That's the important part. Now it means that if we have an equation involving two unknowns, we can all of a sudden solve for both unknowns despite the fact we only have one equation. An example being, I'll just take one straight from the book, 2x plus 3yi equals minus x minus 6i. Now what we want is to put on the left hand side all our unknowns. So everything to do with x and y over here, and everything to do with real numbers or constants over on the right. Okay? And that way, if we have an equation with x and y on the left hand side, and an equation involving, an expression with x and y on the left, and an expression with with constants on the right, we can equate them. So the real parts are equal and the imaginary parts are equal. Alright, so let's get everything with x and y on the left. So it becomes 3x if we bring this x over. plus 3yi equals minus 6i. Okay, now the real part on the left is 3x, and the imaginary part on the left is 3y. What is the real part on the right? Zero. The real is 0. And the imaginary is neg 6. So we can say, therefore, 3x equals 0 and 3y equals minus 6. So the imaginary parts are equal and the real parts are equal. Okay? Now with the practice questions you're about to go through, remember the end game if you like. Our end game is to get x and y on the left, all the constants on the right, and then equate real and imaginary. So the real parts are equal and the imaginary parts are equal. Alright, there's only 2 questions. Page 49, question 1 and 2. All. And this won't be the only thing we do this lesson. Soon I want to move on to the discriminant. There is 10 questions, so go through them quickly. So take an example. How many of you reached C? Just did? And having fun? Have you? Alright, with C, x plus yi, 2 take I. Alright, we'll do this quickly. So we have 2x take xi plus 2yi take yi squared plus equals 8 plus I. Alright, now that we know is minus 1. So it becomes 2x plus xi plus 2yi plus y equals 8 plus I. Now I find it... Huh? What have I done? Yes, thank you. Now I find it helpful to group the real and imaginary parts on the left. So our real parts are these, the 2x plus y, and then our imaginary parts are minus xi plus 2yi. Now to make it very clear for us, we can take out a common factor of I from the imaginary part, leaving us with the real stays the same. But what we do really is just take out I as a common factor. Now our real part on the left is that, because it's not associated with the I. And our real part on the right is the 8. So 2x plus y equals 8. Now our imaginary part on the left is the coefficient of I, and the coefficient of I is that. And the coefficient of I equates, so the coefficient of I on the left is equal to the coefficient of I on the right. And the coefficient of I on the right is 1. Go away. Leaving us with this equation of minus x plus 2y equals 1. Now, what we have here is a beautiful little simultaneous equation. Any ideas on how to solve? And remember, when I'm asking solve, it doesn't have to be algebraically. There are maybe 2 methods for algebraically and one with the calculator. 2 ways with the calculator. Alright, So an algebraic way would be to take this line, if we call that line 1 and line 2, take line 2 and multiply the whole of line 2 by 2. So our line 1 stays the same, 2x plus y equals 8. Then this whole line is multiplied by 2, so it becomes minus 2x plus 4y equals 2. Yeah? I'm not sure how you've been shown these before, but is this similar? Yep. And then you do line 1 plus line 2, and that will give you 0 plus 5y equals 10. Therefore, y equals 2. And then you take your value of y as 2 and substitute it back into, I go back into line 1 because it's nice and easy. You'd say, so 2x plus 2, because that's come from here, equals 8. 2x equals 6, x equals 3. That's one algebraic method. Another algebraic method would be to get y by itself, or x by itself. So for example, taking line 1, we would write y equals 8 take 2x, and then we would substitute that into line 2. So it becomes minus x, that's not an x, minus x plus 2 lots of y equals 1. That's come from there. Alright, and then we solve for x. Or the other way, which given the layout of the equation we had at the start, I would go for is calculator. Where's my calculator? And in your calculator, have you all used simultaneous equation mode? Alright, simultaneous equation mode. Let's see if I make that bigger. God. That's tiny on the board, isn't it? Better. Is that? Then we want simultaneous, so F1. And we have essentially AX plus BY equals C. And from our original equation, oh god, no, our A is going to be 2, 1, 8, minus 1, 2, 1. So 2, 1, 8, minus 1, 2, 1. 2, 1, 1, 8, minus 1, what was it, 2, 1. And then we ask it to solve. 3 and 2. Yeah? Alright, so be aware you will come up against simultaneous equations. Because it doesn't say algebraically, you can use whatever method you like to solve them. If you are using the calculator, be careful of which coefficients you enter in. Alright, keep going. Oh yeah, but graphing just takes more rearranging. If it comes out as that, if it comes out as all nicely rearranged for you, might as well go simultaneous. Yeah. Good. 2, 4, 6, 8, 10, 3, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 23, 24. Who else is away today? Multiply it's like 2 times y times I squared. So it becomes 2 times y times minus 1. Yeah, minus 2y. Yeah. So just keep that times the no real bugs. Yes, blue. And then you have 2x 3y equals 1. It'll be a simultaneous equation. How's it going? Yeah, so what he's doing is trying to get together and everything. C, D,
I'm just doing it my way.
What we're trying to do is get as much money as possible. Yeah, so we can both of those. Yeah, the best way to show that is to take these factors of y Yeah, exactly. Okay, that's correct. And now we can divide through the 2x. So minus x is 2y, 2x equals 1. And take another common factor. And then you have some
Make another common factor of like this thing. How you said the same question. You get x and y on one side.
Yeah.
So you just divide by 2y. Just take that.
Well, there isn't a Oh, I see it now.
No, you just say get that on the right, the left-hand side, and get the others, the imaginary readings on the left, right side. So you just divide by 2.
Yes.
Not that one.
And then you still have the
But still,
no, you're sure it's not going to but going forward.
Well, no, I mean, like that.
Well,
Divide by that.
yeah. But what is it?
Yeah, then you do it. Because, you just start moving the x. Right hand side is not at the end of that.
Okay, you're taking more.
I just went, like, feel like simultaneous equations. Just like, yeah, I know how to do that. And then I was doing that. And then I was done and went, from that. It makes sense.
Yeah, well, that makes sense. Right, so you expand the two. What? Where's the two? Is that an I or a 1? Isn't it the 1 there? In the question? No, check it. Yeah. That's why some people go with curly eyes, sort of really differentiate from one. Oh, we've got like just a quarter eyes. Yeah. Not really. You're still going to have to do an extended sort of foil. I guess one reason to put it there is to do it in this way. That's not at times. It's a very strange way to put a bracket. It would read equally well as x plus 1 minus yi. It's not that the x plus 1 is times by the yi. It's just... I don't know. Maybe they're confusing, but really it's a bracket. Two terms, 2 in the i, and a bracket 3 terms, the x to the 1 and 1 to y. And when you expand it out, it turns out 6 x. Yeah.
I think that is better.
So what we're doing now is the reason we're taking it is because you can see it's coefficient equal. So 3y plus 2x so the reason we're taking it out is just so we can really see it coefficient.
The answer is
Oh, there you go.
doing exercise 9.2.
Will I get it?
Simultaneous equations. As soon as you get to question C, you've got to simultaneously equate these. How do you do that? I can see it's not hard, it's very
What I like to do is get all the visual so we've got all the X and Y. You know the right real imaginary parts of this side together. 2x and y don't have an so if we write those here, that's and the imaginary side is x and y. From this side, we can take out one factor on y. 2x, y.
Wait, which one are we doing? 49.
Those two.
Can you go slightly over?
Yes, sure. Give me Asian Sorry, okay. What bit did you leave at?
I think it was.
About to divide by 0? Okay.
Yeah.
Alright, well, I'm afraid that's the proof you want to read through later, but I guess the important
Yeah,
part.
that's the proof.
Alright, the important bit is if we have a plus bi equals c plus di, the real parts are equal and the imaginary parts are equal. So a equals c and b equals d. So if we had, say, x plus y I and that equaled 3 plus 2i, then we can say that x equals 3 and y equals 2. So the constant, or the real terms, are equal, and the coefficient of I is 2. Alright? Now, that means we can solve for x and y just using one equation. Let's do c, because c is quite involved. Now, there's a couple of different ways to do it, but what I like to do is eventually we want to get all the x's and y's on one side, and all the constants on the other side.
What? That's because I was doing that instead of the
Good bit before there, so 2x minus xi plus 2yi minus yi squared equals 8 plus I. Now the tricky part there is the I squared. Do you remember what happens with it? Minus 1, so it becomes minus y times minus 1. Now, you see how here we grouped the reals sort of on the left and the imaginaries on the right? That's what I like to do because it makes the notes visually easy. So our real terms are the ones that don't have I involved. That's the 2x and the y. So we have 2x plus y. Here we have minus I plus 2y equals 8. Now what we can do is essentially take a common factor out of here, and we take out the factor of y, leaving us with minus x plus 2y. So if that expanded back in, it would look exactly like that. So the reason we do that is so that we can see the real term is there. So 2x plus y equals 8. And the coefficient of i's are equal. Because here there's I, its coefficient is that whole thing. And that's equal. And now we have two equations. That being 2x plus y equals 8. That's the real part. That's like that there. And then we have minus x plus 2y equals 1. Okay. Now the question is how to solve from here. Yeah. How well do you remember simultaneous equations? No, not really. You could, but I don't think that would work every time. There are a couple of ways. Yeah, because there's no x squared. One way we talk about is if you label the equations 1 and 2. Yeah, there's... Good. So for example, we could multiply term 2 by 2. So 1 would still be 2x plus y equals 8. If we multiply this whole line by 2, we have minus 2x plus 4y equals 2. And then we add them together. So then we do 1 plus 2. And those cancel, leaving it with 0 plus 5y equals 10. Substitute back in. Or the other way would be to take one of these equations, so that one, and write it as y equals 8 on 2x. And then take that y, substitute into the next equation, so minus x plus 2 lots of 8 on 2x equals 1. And then solve for x. Yeah, and then solve for y.
That takes so much longer.
It does. Or you can use your calculator. So your calculator in equation mode, they have something called simultaneous equations. And number of unknowns is 2. Clearly used it before. But what we have after that there. So as long as the x and y's line up, you go 2, 8, minus 1, 2, 1. So x is 3 and y is 2. No, if it just says solve, then fine. But if it says algebraically, then yes, you have to use one of these two. If it just, otherwise, that's fine. However, it's good to know, I know this is quicker, but this always works. Alright? Because it's not always possible just to do it times by 2 and then cancel nicely. And when we come to question 2, when you go to question 2, you'll need this substitution. Because neither that or the calculator helps you. It has to be on this.
How do you times
Right, so if you have, say, 3 times a fifth, you write it as 3 over 1 times 1 over 5. Yeah. And when you're multiplying, you multiply across the top.
Oh, so I thought you had to like get the denominator.
Yeah, common denominator is when you add and subtract.
Oh, so when it's added, you just
Yeah, you times it. So if you were going to times this out, it would become minus x plus 16 over 2x equals 1. And then, that's not particularly easy, is it? Then I'll go add a 1. Use multiply top down by 2x, so it becomes minus 2x squared over 2x plus 16.
That works, thank you.
You're right, this way takes longer. Yeah, it's all great. That's nice. But when this fails, go with this. Yeah, start. The first couple A and B are easy. See what to get to the goal. There is it. What? B? 2B. Huh? I'll be with you in a sec.
I don't think it's right. It feels like it could make sense.
Alright. Sorry, I was going to just interrupt you. I'll let you get back to that. But some people are starting to finish the imaginary numbers questions. So instead of them getting bored, I thought I'd teach the next section. And the next section is the discriminant. I haven't typed that particularly clearly. So if you could flick to your notebooks and write in the discriminant. I'll type it there so you can actually see my writing. And I'll give you time to do the questions in a sec. It's going to be an and.
Were you checking my stuff?